Thank you very much, Chairman, for the kind introduction. I'm Wen-Chung from Cheng University. First of all, I would like to thank the organizing committee, Professor Yong and Professor Wang, for giving me this chance. And it's my great honor to share with you our recent result here. So the title of my talk today is Fluorescent Electrospun Nanofibers for metal ion sensing applications. Okay, before getting to our research work, I would like to just use several slides to share with you our campus. So my university is National Cheng University and located at the southern part of Taiwan. It's located at Tainan. Okay. So it's actually at the southern part of Taiwan. It's just a little bit north of the second big city in Taiwan, which is called Kaohsiung. Okay, and our campus is located at the downtown area of Tainan, just close to the main rail station. Okay, so our main campus is around divided into 7 sub-campus, and we have law school, hospitals, and medical school, science school, engineering schools. Okay, so this is our landmark. It's a banyan garden. Okay, so this banyan tree has age over 100 years. And we have a very small little lake called Cheng Lake. And this is our department building. It's a 12th floor building, just located at the east part of our campus. Okay, so let's go back to our my scientific part. So before getting into our research work, I just want to give you a quick introduction to reveal the rationale why we devote ourselves to fabricate fluorescent sensing nanofibers for metal ion sensing applications. So traditionally, fluorescent molecular sensor is composed of 2 major moieties. The recognition moieties can specifically bind with various types of ions, such as metal ion in wastewater, volatile compounds, organic compounds, or explosives. And the fluorescent moieties will transduce this binding into fluorescent signals. Traditionally, the fluorescent molecular sensor works in dilute solution, and it is difficult to separate and recycle the sensor for multiple use. Application of sensor devices based on the morphology of thin film or membrane morphology may overcome this problem. However, the limited solid-liquid interface and poor mass transfer may cause low sensitivity. Therefore, we try to propose the fabrication of fluorescent sensing nanofibers based on electron spinning technique to gain more higher specific surface area as novel sensing devices. So the electron spinning technique is a popular way for fabrication of polymeric nanofibers with diameters in the range of several hundred nanometers. The basic setup for electron spinning is composed of a high voltage power supply, a spinnet, and a collector. As the cylindrical pump pushes the polymer solution through the spinnet, the electric field between spinnet and the collector will conquer the cohesive force of polymer solution and result in the weakening and the formation of a fibrous composition. And then the 4D nanofiber will be collected on the collector. So the morphology of a 4D nanofiber could be manipulated through the controlling of processing parameters in 2 major categories: the intrinsic property of polymer solution and the operational conditions. In the following slide, I would like to share with you our recent research work, okay, in 3 different fluorescent sensing nanofiber systems. In the first part, we simply physically blend a random copolymer with a fluorescent sensing compound, and through the electron spinning technique to prepare the blending nanofibers for metal sensing application. In the second part, instead of a physical blending, we turn to look for the chemical attachment of fluorescent sensing moieties onto the nanofibers for sensing performance. In the third part, because of the sensing ligand we use in the second part, the bipyridine ligand can bind with several different kinds of metal ions and shows very complicated fluorescence response. So in order to get a better selectivity and well quantitative analysis, so we choose another sensing moieties based on rhodamine moieties and try to study their sensing performance for copper ion sensing. So in the first part, we simply blend a random polymer polyhema called MMA with fluorescent sensing bipyridine fluorine bipyridine compound to prepare the blending neurofiber. This fluorescent sensing compound is composed of fluorescent moiety and the two bipyridine metal ion chelating moieties. After binding with metal ion, the change in charge transfer effect will result in difference or shift in the fluorescent characteristic, such as color change or fluorescence quenching. This random copolymer is composed of hydrophilic moieties hema for good swelling of water in aqueous solution, and also the thermally cross-linkable MMA moieties for retaining the fibrous conformation in aqueous solution. So use the blending solution of copolymer and the sensing compound for the electron spin to prepare the blending nanofibers. We'll first investigate the intrinsic sensing performance for this fluorescent sensing compound in organic solvent. After binding with different type of metal ion in assessed amount, we observe three typical fluorescence response. First, partial fluorescent quenching without any shift in spectra. Second, partial fluorescence quenching with red shift in emission maxima. Third, complete fluorescence quenching. So in order to get more clear idea, so we chose three different metal ions to study the fluorescent titration behaviors. For zinc ion titration, with increasing ion concentration, we first observe partial fluorescent quenching without spectral shift at a low ion concentration, and then further fluorescent quenching with an additional band showed up at a moderate ion concentration. Finally, the emission peak completely shift to this additional band at high ion concentration. For the mercury ion titration, we observe a similar fluorescence response, except for the additional band showed up at a much higher ion concentration. For the copper ion titration, we just observe the fluorescent quenching without spectral shift with increasing ion concentration. So the next slide shows you the SEM image of morphology of electron spun nanofibers, which were prepared by using two copolymers with different molecular weight and one blending of P2 copolymer with 5% of fluorescent sensing compound. Okay, and for the spun nanofiber, we observe the average diameter for P1 nanofiber was around 250 nanometers. But for the P2 and the P2-5 blending nanofibers, the average diameter were around 500 nanometers. So the smaller diameters, smaller size for P1 nanofiber could be attributed to its lower molecular weight and thus lower viscosity for its polymer solution. Without thermal cross-linking treatment, this nanofiber cannot maintain their morphology, fibrous morphology after immersion in aqueous solution. However, after the treatment, thermal cross-linking treatment, these nanofibers only with the higher NMA content can remain their fibrous conformation in aqueous solution with good swelling of water to a much larger diameter, around 1 micron. So then we study the fluorescence titration behavior for this P2-5 blending nanofibers against three different types of metal ions. For the zinc ion titration, with increasing ion concentration, we observe partial fluorescence quench with a red shift in emission maxima. from 450 nanometer to around 520 nanometers, which corresponding to a color change from blue to green. For the mercury ion titration, similar behavior was observed, except for the less redshift to only around 485 nanometers. So this is corresponding to a color change from blue to blue-green. For the copper ion titration, with increasing ion concentration, we only observe complete fluorescent quenching with very little spectral shift. And from the confocal images of this blending nanofiber after immersion in aqueous solution without metal ion with accessible amount of mercury ion or zinc ion, we could observe a visually distinguishable color change from blue to blue-green or from blue to green respectively. In addition, this blending nanofiber could be regenerated by the treatment with chelating agents such as EDTA to remove the binding metal ions. So even though in the first part we have demonstrated the preparation of fluorescent sensing nanofibers by physically blend the fluorescent sensing compound in the nanofibers. However, the potential leakage of these fluorophores from nanofiber may cause a problem or concern in long-term stability. Therefore, in the second part, we look for chemical attachment of fluorescent sensing moieties onto the nanofibers. So here we random copolymize 3 types of monomers to integrate hydrophilic lipon moieties, physically cross-linkable SA moieties, and the fluorescent sensing FBP1 moieties into a random copolymer, then through the electrospinning to fabricate its corresponding nanofibers for metal sensing studies. Okay, so here we prepare 3 random copolymer with different compositions. This table shows the chemical structure and the thermal properties. The SEM images shows the morphology of these electron spun nanofibers in different states. For the X-spun nanofiber, the average diameters were around 250 nanometer, and after immersion in aqueous solution, it can retain the fibrous conformation with good swelling of water to a larger diameter around 1 micron. And to study the sensing performance for these random copolymers, we choose P2 copolymers and study the PLO spectrum in organic solution first. And after binding with assessment amount of different types of metal ions, we also observe 3 typical fluorescent response. First, after binding with zinc and the mercury ions, the fluorescence was partially quenched, and the emission peak redshift to a longer wavelength. This is probably due to the formation of coplanar complex. Second, after binding with ferric or copper ions, the fluorescence was also partially quenched with a redshift in emission maxima, and this is probably due to the formation of non-coplanar complex. Third, complete fluorescence quench after binding with copper or nickel ion, and this is probably due to the photo-induced electron transfer behavior. So we just choose one type of metal ion, so we choose zinc ion to study the sensing performance of P2 random copolymer in 3 different states: dilute solution, spin-coated thin film, and electron spun nanofibers. The fluorescent titration shows similar fluorescent response. With increasing ion concentration, we observe fluorescent quenching with redshift in emission peak. However, the sensitivity toward ion concentration was different among 3 states. We observed the best sensitivity for dilute solution, slightly poorer sensitivity for nanofibers, and the worst sensitivity for the thin films. Okay, so by comparing these 2 solid states, we can find that our nanofiber shows much higher sensitivity against thin film. This could be attributed to their high specific surface area of nanofiber conformations. And in the third part, because of the bipyridine we showed you before, can find with several different kind of metal ion and show very complicated fluorescent response. So in order to get a better selectivity and more quantitative analysis, so here in the third part we turn to integrate another well-known fluorescent sensing ligand, or rhodamine, into the nanofiber. So the sensing mechanism for rhodamine-based moiety is through the spiral rectangle ring opening process. So before the addition of either proton or copper ion, this moiety is colorless without absorption in visible region and also shows no emission, no fluorescence. After protonization, the ring is open and this turn on strong absorption with pink in color and also a strong fluorescence intensity. However, if combined with a copper ion to form this complex will only show strong absorption with pink in color, but the fluorescence will be quenched due to the paramagnetic effect of copper ions. So in order to build up an on-off type sensor, so we first activate the absorption of fluorescence in acidic condition and then quench the fluorescence by addition of copper ion. And this fluorescent quenching will be quantitatively analyzed. So here we also synthesize 3 different polymers with different composition. This table shows their chemical structure and the thermal properties. From the UV and the PL spectra of these 3 random polymers in aqueous solution in acidic condition, we can observe the absorbance increase with increasing rhodamine content. However, the fluorescence intensity was significantly quenched for PNR1 copolymer with highest rhodamine content composition. This might be due to the possible aggregation of rhodamine moiety at such high composition. So we just choose the PNR2 random copolymer with the moderate rhodamine content for further study their sensing performance. So the SEM image shows if we through the electron spin to prepare the electron spun nanofiber, the morphology of nanofiber in different states. So this is the S-spun nanofiber. Diameter was around 200 nanometer. After thermal cross-linking, there shows no significant change in conformation. After immersion in aqueous solution, the nanofiber could maintain their fibrous conformation with only with a good swirling of water to larger diameter, around also 1 micron. And from the UV and the PL spectra of our PLR2 nanofiber at a different pH value, you can see the turn on of fluorescence, turn on of absorption, and the turn on of fluorescence at a pH value lower than 4. And from the plot of absorbance and the fluorescent intensity as a function of pH value before and after addition of copper ion, you can see that after binding with copper ion, the absorbance can be turned on even at high pH value. However, the fluorescence was quenched after the addition of copper ion. Okay, so in order to get a clear on-off ratio between before and after addition of copper ion, so we choose pH value around 3.6 to further study the fluorescent titration behavior. So here again, we also study the fluorescent titration behavior of PNR2 copolymers in 3 different states: dilute solution, deep coated thin film, and the electron spun nanofiber. And a similar fluorescence response were observed for among these 3 different states. Okay, so with increasing ion concentration, we can see the fluorescent quenching with very little spectral shift. However, again, the sensitivity were different among these three different states. So in order to get a quantitative comparison, we construct a Stern moment plot. From this plot, we extricate the Stern moment constant from the slope. So we can quantitatively compare the sensitivity among these three different states. So from this table, we can conclude that the sensitivity for the polymer in dilute solution and with the conformation of neural fibers are similar, and which are much larger than the sensitivity of the polymer in thin film conformation. And from the selectivity and the computation test, we concluded our rendered copolymer shows very good selectivity against metal ion and without the interference by other types of metal ions. And again, our nanofibers could be regenerated through the treatment with chelating agent repeatedly for many cycles. So in conclusion, we share with you that we demonstrate the application of fluorescent sensing nanofibers for metal ion sensing applications. And the sensing moieties could be either physically blend into or chemically attached onto the neural fibers. The sensing performance for the neural fiber could be adjusted either through the change of chemical structure of sensing moieties or through the manipulation for the electron spinning technique. And finally, I would like to thank for the support from different projects, my collaborators and my hardworking graduate students. And most of all, thank you for your kind attention.